Hi there, welcome back. In today's class, we will go into a little bit more detail for what concerns the Wang transform that we introduced last time. We will see that this transform is actually quite useful to understand the connections between the different probability measures we may play with. Until now, we have just considered the probability P, the physical measure, the probability Q, the risk-neutral measure, and the probability D, the share, stock, or price measure. Now, later in the course, we will introduce other probability measures, like, for example, the forward measure. And in all these situations, at least until we play with Ito processes, the Wang transform is rather useful. It is useful because it allows us to actually quantify the error that we introduce every time that we change a measure. Why an error? Because we know, for example, if we consider P and Q, that P and Q are equivalent. It means that they agree on what is not possible. So if something is impossible on the P, it has probability 0. And it will have probability 0 also on the Q. But if something is possible on the P, it may have a probability of, say, 20%, and on the Q, it could be a probability of 80%. So if the probability Q, the risk-neutral probability, is used for pricing, a legitimate question is there an impact for this price when then I use this information in the real world, where the real probability measure is the physical measure? Now, in the very simple Black-Scholes framework, is actually quite easy to verify, identify, and assess the error. And we will see, for example, that in Black-Scholes, risk-neutral pricing plays with a probability that tends to underestimate the probability of being in the money at maturity. So this is good news for us. There are other situations in which, for example, we might have an opposite behavior. And using the Wang transform, for example, we can try to understand this. In this class, we will also see that Wang transform in reality is nothing more than what, in another field of statistics and probability, is the Lorenz curve, or to be more exact, either the Lorenz or the line-Köhler curves that are used in inequality studies. The difference between the two curves lies in the convexity and the concavity, as we shall see. But let's say that most of the results are essentially the same. So let's start and let's try to understand a little bit more why looking at the Wang transform can be useful for us. Okay, so last time we briefly introduced the concept of distortion function. Now, what is a distortion function? A function g, so we will use g, is a distortion function for us if it maps from the unit interval 0, 1 into the unit interval 0, 1. So the argument of the function is a quantity between 0 and 1, and the function gives us a number between 0 and 1. And moreover, the function needs to satisfy three very basic characteristics. G of 0, so the function in 0 is equal to 0, G of 1 is equal to 1, and the function is non-decreasing. So it starts in 0 and then it grows towards 1. How it grows is not particularly relevant for us at this stage. It can be a concave function, it can be a convex function. So in the little plots that you see on your screen, obviously these functions are just drawings, you can see different possible behaviors. Our function will always lie in terms of graph within the so-called unit square. Okay, so it's the square where each edge is just 1 unit. Okay, so our function is there. This square, this graphical representation, will be quite useful in a minute. Now, why are distortion functions relevant to us? They are important for us Because thanks to the distortion function, thanks to the use of distortion functions, I can actually generate a new probability measure starting from an existing one. How? Let's see the following. Okay, imagine that we have a probability space, the usual one, omega f p. P can be, for example, our physical measure, but at this stage we are not yet giving any particular meaning to the different probabilities. So on your screen you can already see P and Q. Let's say that in a minute they will be the physical measure and the risk neutral measure, but for the moment they are just two different probability measures. Okay, if we consider an event E in the sigma algebra F, under P, the probability of this event will be P of E, very simple. Now, this number is a number between 0 and 1, so it can be the argument of my distortion function G. And actually, what happens is that if I apply G to the probability of E, what I get is, again, a number between 0 and 1, because it's a distortion function that I'm using. So what I can do is to define the probability Q of the event E as G applied to the probability P of the event E. Now, what I leave to you as an exercise is to verify that, first of all, the probability Q is well defined. So just check its properties as we did when we were introducing the Radon-Nikodym derivative as a way to change measure. And after verifying that Q is a proper probability measure, what you can try to do is to verify that actually, thanks to the distortion function G, the probability P and Q are equivalent. So this is very important. Now, once we have distortion functions, once we have distortion probability measures, we can then consider, for example, distortion risk measures. Now, risk measures are not an important part of our course. It will be an important part of the other course I'm teaching at this moment, that is to say quantitative risk management, but it's nevertheless interesting to observe the following. So if I consider a random variable x that is a non-negative random variable, and in risk management, typically you consider losses to be positive quantities so that profits are negative quantities. Why this? Because in risk management, typically you play with losses, so you want to minimize losses, and taking losses to be the positive quantities simplifies a little bit the formulas because you get rid of the minus sign, okay? Obviously, if you are investing, typically profits are positive and losses are negative, but in the risk management framework, we are a little bit pessimistic, not optimistic, so we are a little bit pessimistic, and we look at losses, so these are the positive quantities for us. Okay, if x is a loss random variable, and we assume that f is its cumulative distribution function, and I define S 1 minus f to be the so-called survival function, I can always introduce a distortion risk measure, which is what I call here rho of g of x, which is nothing more than the expectation under the measure Q of my loss random variable x. Now, if I expand this expectation, as you see on your screen, this expectation is nothing more than the integral between 0 and plus infinity, because I'm considering a non-negative random variable, so profits are out of the game here, of what? Of g applied to the survival function of x under the probability measure P. So, in other way, is the integral between 0 and plus infinity of g of s of x, where, again, s of x is 1 minus f of x, where f of x is the CDF of my random variable x. Now, why it is interesting to briefly say this? Because if I consider properties of the g function, for example, I know that if g is a concave function, then my risk measure is coherent. If g is convex, conversely, my risk measure is not coherent. These are things that, again, I repeat, for us at this stage, if we have the time, maybe we will say something at the end of the course. But at this stage, they are not fundamental, but it's always nice to know something about these things. Coherence for a risk measure means that our risk measure, which is nothing more than a function that we use to evaluate risk, so to assess the risk of something, for example, the risk involved in the investments we have in a portfolio. So this function is called coherent if it has four useful mathematical properties. That is to say, it is monotone, it is translation invariance, it is positive homogeneous over the one, and it is subadditive. Now, these are all things that, if you also attend quantitative risk management, will be clearer. Otherwise, it's not a big deal. Okay? If you choose the appropriate function g, actually many of the risk measures that we see in risk management are actually replicable. So we can obtain the different risk measures like objects linked to specific distortion function. A very simple example is the valid risk, or VAR, which is nothing more than the quantile is nothing more than a quantile of the loss distribution. So, for example, if I choose my g to be a function which is 0 for the argument being between 0 and 1 minus alpha, and 1 when the argument is larger than 1 minus alpha and smaller than 1, then if I apply this function, I get a quantile of the loss distribution. So I will get the quantity such that alpha percent of all the observations are smaller and 1 minus alpha percent are larger. And similarly, I can obtain the so-called expected shortfall, which is nothing more than the expected loss above a given VAR level. So if I compute a given valid risk at a given confidence level, I get a quantile, and then I might be interested in knowing what is the expected loss when I'm above that quantile. So let's assume that we have computed the valid risk to be 10 million, and let's assume that this 10 million is the 95% valid risk. It means that 95% of the times we can expect our portfolio to generate losses that are smaller than 10 million and only 5% of times larger than 10 million. But larger than 10 million can be insufficient as an information, because larger than 10 million can be 11 million or can be 20 billion. So what we can do is try to have an information about the expected loss above that 10 million threshold. And this is the question answered by the expected shortfall. So maybe I compute an expected shortfall of 12, or maybe I compute an expected shortfall of 200, okay? And that gives a little bit more information about the tail of the loss distribution. But again, this is not particularly relevant for us. It's just to show you that financial mathematics and risk management are not two independent fields. There is always a very strong connection among the different fields, also because in financial mathematics we are, for example, interested in pricing and in looking at the positive side of our investments. Risk management just plays the opposite role. So try to look at the bad side of our investments, try to minimize losses, okay? Good. Now, put aside for a second the concept of distortion function, so our function g. Now I want to introduce to you another function that is rather important and that was introduced in 1905 by Max Otto Lorenz. This is a function that is known as the Lorenz curve in inequality studies. Now, why do we care about inequality studies in financial mathematics, because actually we will see that the Wang transform represents a special type of Lorenz curve, and this is very useful for us. Now, the Lorenz curve is a curve that can be drawn in the unit square. Okay, so we are looking at the unit square. In this curve, we have two important elements. P is what? P is the percentage of population that we are considering once we have ordered all the members of a given economy from the poorest to the richest. So imagine that we are considering an economy made of 100 people. These people will have different levels of wealth or income. And what I do, I will just order these 100 people from the poorest to the richest. Okay? So that if I set P to be equal to 0.2, I'm just considering the first 20% of people. So if you want, the poorest 20% of the population. And 1 minus P will be the remaining part, so 80%, and this will be the 80% of the richer with respect to the poorest. And P, naturally, representing this percentage of the population, will be between 0 and 1. Now, imagine that I have my economy and I have the population of the economy. So I can obviously order the different individuals in the population from the poorest to the richest. And then I can also ask myself the following question. If I consider the total wealth of the economy, so I consider the wealth of every single individual and I sum everything together, or if I consider income, I can do the same with income. The question is, if I consider the first 20% of the population in terms of their wealth, what total amount of the whole wealth of the economy do they possess? So the Lorenz curve is nothing more than the curve that tells me that for the first X% of the population, or for us, for the first P% of the population, I have an amount LP% of the total wealth. Okay, so it's a curve that starts in 0, because obviously when I consider nobody, so if there is no individual that I'm taking into consideration, the total wealth in the hands of no one is 0. And on the opposite, when I consider the whole population, so I consider all the individuals together, obviously all the individuals together will have all the wealth in the economy. So the opposite situation is L of 1 equal to 1. Okay? Then what do I have? This curve is a curve that links the percentage of population to the corresponding percentage of the total wealth that is in the hands of the first percentage of the population. Now you can imagine that necessarily this curve needs to be non-decreasing, because every time I'm increasing the percentage of the population that I'm considering, it makes sense that the wealth in the hands of that percentage cannot be lower than the wealth in the hands of a smaller percentage of the population. So this function needs to be non-decreasing. And we can also show analytically that this function needs to be convex. Now, this function, the Lorenz curve, also has two interesting limiting situations. So if you want, let's consider two opposite types of economy. Let's consider the so-called communist economy and the so-called tyranny. Now, in the communist economy, every single individual owns the same amount of the total wealth. Okay, so if we have 100 individuals, let's assume that the total wealth is as well 100. In the communist society, every individual owns one. So if I consider the first 1% of the population, it means one individual, and I can order them as I want, because in any case, they all have the same amount. So I can permute them as I prefer in ranking them. So if I consider the first 1% of the population, the first 1% of the population owns 1% of the total wealth. Because the total wealth is 100, the first guy owns 1, which is 1% of 100. If I consider the first two guys own 1 plus 1, 2 of the total wealth, which is 2%. So in the communist economy, every percentage P of the population corresponds to a percentage LP of the total wealth, which is actually P. So it means that if I draw my Lorenz curve for the communist society, I will consider the diagonal of my unit square. So it's a function that starts in 0, ends in 1, and then it's just a straight line corresponding to the diagonal of the square. This is the so-called Lorenz of perfect inequality, LPE. The opposite situation is what we call tyranny. In tyranny, we assume that we always have a population of 100, but now all the wealth is in the hands of one single individual, the king, the emperor. All the others own 0, nothing. Now, the 0 is not necessarily a real 0, can also be a relative 0. So we can say that 0 represents the nearly basic level to survive, but nothing more, okay? So if we consider excess wealth as the wealth above this minimum level for surviving, we are considering a situation in which just one guy owns everything, the king, the emperor, and all the others, nothing. So what happens? If I order my population from the poorest to the richest, I will have a long sequence of zeros because they own 0, and one guy will own everything, so 100. So in that situation, my Lorenz curve is a curve that coincides with the x-axis for all the individuals apart 1, and for the last observation, when p is equal to 1, jumps to 1, because only one guy owns everything. So is the line that you see dashed on the screen, and that we call LPI, the Lorenz curve of perfect inequality. Now, every Lorenz curve of whatever economy needs to lie between these two opposite situations. So every Lorenz curve needs to lie in the smaller, so not in the smaller, in the lower triangle of the unit square. Okay, so it will have as an upper bound the perfect equality line, and as a lower bound the perfect inequality line. For the rest, it will be a non-decreasing convex function in this triangle. Now, an interesting measure that we will discuss in a minute in more detail is the so-called Gini index. The Gini index was introduced in 1912 by Corrado Gini. It's one of the many measures that we can use to understand how equal or unequal a given society is. I'm not a particularly great fan of Gini as a measure of inequality because it has its own problems and characteristics that are often ignored, but it's nonetheless a very useful measure, as I will tend to show you in a minute. Now, the Gini index is an index that is between 0 and 1, and is an index that, geometrically speaking, then we can also give the analytical representation, but geometrically speaking, represents 2 times the area A that you see on your screen. So consider the Lorenz curve that is drawn as the red convex line in the lower triangle of the unit square. This is our Lorenz curve, okay? Now, this Lorenz curve needs to lie between the perfect equality and the perfect inequality. What I can do is that I can always compute, I can always estimate the area that lies between the perfect equality line and my Lorenz curve. And I call this area that is in green on your screen A. Okay, this area can be between 0 if my Lorenz curve coincides with the perfect equality, and 1/2 if my Lorenz curve coincides with the perfect inequality, because the area I'm considering is the lower triangle, which is 1/2 of the unit square, and the area of the unit square is 1, okay? Now, if I take this quantity A, I can always take the ratio of this quantity A over 1/2, which is the total area of the lower triangle. That is to say, I can take 2 times A, because A divided 1/2 is like 2 times A. Okay, 2 times A is our Gini index. The Gini index is a number between 0 and 1. Clearly, when Gini is equal to 0, it means that my Lorenz curve coincides with the perfect equality line, so the area A is 0. When, conversely, the Gini index is equal to 1, it means that A is equal to 1/2. So 2 times 1/2 equal to 1, and that is the situation in which the Lorenz curve coincides with the perfect inequality. So, in an economy where the Gini index is equal to 0, we're essentially considering the communist situation. In an economy in which the Gini index is equal to 1, we are considering the tyranny, okay? So, and this index, all the other values, will tend to give us different combination of the wealth within our economy among the individuals. Notice that we can have several Lorenz curves, it's not difficult to see, also from an intuitive point of view, that share the same Gini index. So this is one of the characteristics that, at least according to me, do not allow to compare economies just looking at the Gini index. Another characteristic is linked to the fact that the Gini index is scale-free, so it's a number between 0 and 1, okay? And if I consider an economy in which the Gini is equal to 0, a communist type society, one thing is if everyone is rich, and one thing is if everyone is poor. So if the fact that everyone owns the same is not necessarily a good thing, because I can consider a society in which everyone owns the same, but they own essentially nothing or almost nothing, because the total wealth of the economy is ridiculous, or a society that, looking at the Gini, seems much more unequal, so in principle a worse type of society, yet it looks very unequal because we have Bill Gates and Jeff Bezos, but all the rest of the society, in any case, has more than a decent amount of wealth to live a good life, okay? Now, I'm not saying that this is what happens in reality, but we can easily understand that just looking at the Gini index without considering other quantities of the economy can be highly misleading, okay? Because we can tend to say that some country somewhere in the world in which everyone is very poor has a lower Gini than the Netherlands, so that society is preferable with respect to the Netherlands. In the Netherlands, we have a certain amount of inequality, as in France, as in Germany, as in Italy, as in the US. But we also have a different amount of wealth, and while we have too many poors, and this is something that is unfortunately there and for granted, that cannot be denied, is not necessarily a higher Gini that represents a bad society. So we need more measures, but this is something that I just like to stress every time. Never trust studies that only use one measure to measure something, okay? Because you always need more information to give a sufficient amount of interpretation to a phenomenon. Now, if you want to be a little bit more formal, I can consider a random variable x, which is non-negative, with a given CDF, f. The only requirement for me is that this random variable has a finite mean, and you understand this is not a big requirement. We are not even interested in the fact that the random variable has a finite variance. So we are not, for example, imposing anything with respect to the second moment. Conversely, we have seen that until now, we were playing with variables whose second moment was, at least in a way, finite, because we want to be able to compute the variance and blah, blah, blah when we play with our running motion. Here, it is not necessary. We are just requiring the mean to be finite. We can then introduce the function q, which is the quantile function. The quantile function is nothing more than the generalized inverse of our CDF. So it's the function such that if we fix a probability, gives us the corresponding critical value for what concerns our random variable. If I have this quantile function, the Lorenz curve at the percentage p, that at the end of the day becomes a probability. So L of p is nothing more than the integral between 0 and p of the quantile function q t dt over the expectation of x. That's why we want the expectation to be finite, because we are rescaling everything by the expectation. So it's very important that this quantity is finite. And I immediately understand by looking at this function L, my Lorenz function, that this is non-decreasing. As I told you, it is convex. It is 0 in 0, 1 in 1. Every Lorenz function, so if I know explicitly the Lorenz function from an analytical point of view, I can characterize the distribution that is related to that Lorenz function. So if I have a Lorenz function, only one distribution can have that specific analytical representation. Why? Because the Lorenz function is defined through the quantile function. And the quantile function characterizes a distribution as the distribution characterizes the distribution itself. So we know that there are different ways of characterizing the distribution of a random variable. One is knowing the distribution. One is knowing the quantile function, from which we can immediately recollect the distribution function. One is knowing the characteristic function, and again, from there I can obtain the density and the distribution. One is knowing, for example, the Lorenz function, obviously analytically. So I know the analytical representation of the Lorenz function of my curve that I can draw in the lower triangle of the unit square. And then an interesting thing that should ring a bell for you is the fact that every Lorenz function is a function that starts in 0, ends in 1, is non-decreasing, and essentially represents itself a CDF. So a Lorenz function can be seen as a cumulative distribution function of a specific random variable, which is not the random variable x, for which my function L is the Lorenz function, is another random variable that in inequality studies has an interesting use, or that, for example, together with co-authors, I have used, for example, in copulas and other things. But it's nice to observe that L itself can be read as a CDF. Now, it's not difficult to observe that if this is the case, so if the Lorenz function is a function that has this property, every Lorenz function is nothing more than a distortion function. And it's a particular type of distortion function, is a convex distortion function. We know that a distortion function can be convex or concave. Lorenz function can only be convex. Okay, I agree with you that when the Lorenz function is the perfect equality line, that a line is both concave and convex. But apart from this very pedantic situation, a Lorenz function is convex. So if we give an interpretation as a distortion function, and we can because it's non-decreasing, 0 in 0 and 1 in 1, it maps from 0, 1 to 0, 1, so it satisfies all the requirements. If it is read as a distortion function, then the Lorenz function is a convex distortion function. So, for example, in terms of risk management, it cannot generate coherent risk measures. So if I use my Lorenz function in order to generate a probability measure, a new probability measure, this new probability measure will be equivalent to the original probability measure. I can build then distortion risk measure by taking the expectation with respect to this new probability measure of my loss random variable. But what I know is that the resulting risk measure is not coherent, so it does not have all the nice properties of coherence. In particular, we can show that one of the properties that drops is the so-called subadditivity. So it means that if my risk measure is not coherent, we end up with a risk measure that does not favor diversification. So if I diversify my portfolio, it's not guaranteed that the risk of the portfolio decreases with respect to just the simple sum of the elements of the portfolio. But again, this is risk management, so we put that aside. If I'm interested in the Gini index, as I told you, the Gini index is this area A multiplied by 2, and if I want to compute that explicitly, is just a matter of computing the distance between LP and the Lorentz of perfect inequality rescaled by the total area that we have in our lower triangle. And again, as I told you, if Gini is equal to 0, it means that my Lorentz curve is the perfect equality line. If Gini is equal to 1, it means that my Lorentz curve is the perfect inequality line. The Gini index can be computed in many, many different ways. So the graphical representation I'm giving you is just one of the different ways. I think that in the literature there are at least 12 different ways of representing the Gini index. You always get the same number, but the different representation allows for studying different properties of the index. Now, let's consider two simple distributions that we know quite well. One is the Pareto distribution, and one is the log-normal distribution. Now, the Pareto distribution is a distribution whose density f of x is what you see on your screen, so it's alpha k to the power alpha divided by x to the power alpha plus 1. This for a value x larger than the minimum value capital K. If I compute the Lorentz curve of a Pareto distributed random variable, it's a very simple exercise. I compute the quantile function, then I integrate the quantile function between 0 and p. I rescale for the average of my random variable, and I get the function 1 minus open parentheses, 1 minus p, close parentheses, everything at the 1 minus 1 over alpha exponent. And once I have the Lorentz curve, I can plot it, okay? And I can compute the Gini index, which is 1 over 2 times alpha minus 1, okay? And since the requirement for the existence of the Lorentz curve is that the mean is finite and the Pareto distribution can have an infinite mean, we need to constrain the value of the alpha parameter. So alpha needs to be larger than equal to 1, because for smaller alpha, the mean of the Pareto is not finite. The other distribution we consider is the log normal. The log normal is nothing more than a log normal in the logs. So the density function is what you see on your screen that we know very well. I can compute the Lorentz curve. The Lorentz curve is capital phi, which is the CDF of a standard normal, computed in an argument which is the quantile function of a standard normal, capital phi to the minus 1, at a level p minus sigma, where sigma is the sigma of my log normal. So it's the sigma parameter of my log normal. That, I stress, is not the variance of my log normally distributed random variable. Sigma is the variance in the normal. So if you want, is the variance of the logs that we consider in the log normal. But in terms of the log normal random variable is not the variance, is one of the parameters of the function that enters in the variance. If you remember what is the variance of a log normally distributed random variable, so the exponential of mu plus sigma square over 2. Okay? So it's very important to recall that. Once I have the Lorenz function, I can compute again the Gini index. And the Gini index is what you see on your screen. So it's 2 times the CDF of a standard normal computed in sigma over the square root of 2 minus 1. Okay? And again, both in the case of the Pareto and in the case of the log normal, the Gini is a quantity between 0 and 1, depending obviously on the value of alpha for the Pareto or the value sigma for what concerns the log normal. As I told you, the Lorenz curve is convex, so it means that it can generate a coherent risk measure. If I want a coherent risk measure, what I can do, I can play either with the inverse of the Lorenz function, that obviously will become concave, or I can introduce another function, which is 1 minus L of 1 minus p. This is again a concave function that is called the Lime-Kühler curve. It's a curve that reads in the opposite way of the log normal. So we do not consider the poorest percentage of the population and then look at the percentage of the total wealth they own, but we order the observations in the opposite way from the richest to the poorest, and we look at how much or what is the amount in percentage of the total wealth in the hands of the top 10%, 20% of the population. So I consider the top 10%, the top 10% is the richest 10% of the population, and look at the amount of wealth they possess. In that case, the curve is concave. And if I use the Lime-Kühler curve, obviously I get a coherent risk measure if I want. Okay, on the basis of what we have just said for what concerns the Wang transform and the Lorenz curve, let's go back to something that we have already seen together, that is to say the connection between P and Q. Now, we start with a very basic Black-Scholes-Merton framework, so we assume a very standard geometric random motion for what concerns the price process of the risky asset. For all the rest remains the same as in our setting, so no novelty at all. But the results, as I will show you later, actually work more in general. So we can definitely change the geometric random motion as a process. We can make it more flexible. We can even totally change the process. And until we stay within the Ito processes framework, more or less, okay, becomes more complicated, but more or less what we are seeing here still holds. Now, we know that under this framework, if I consider the log prices are normally distributed, because in the geometric random motion I have that the prices are log normally distributed, so the log prices are normally distributed. Under the physical measure, this normal distribution is what you see on your screen. So we can always compute that as a normal distribution that has a mean, which is equal to the logarithm of S0 plus mu minus 1 over 2 sigma square capital T as mean. And for what concerns the standard deviation is sigma square root of T. If I want the variance, it would be sigma squared capital T. For what concerns the same object, so the log of prices under the risk interval measure is essentially the same stuff. So it's a normal distribution with the same standard deviation, so it's sigma square root of capital T. But for what concerns the mean is mostly the same as before, but mu is substituted with R. Now notice one thing. If mu is substituted with R, we can safely assume that mu is larger than R. Why? Because we are taking into consideration a risky asset, and we want the risky asset to be, in terms of return, something that gives a higher return than the risk-free. Otherwise, it would be not very clever to play with a risky asset that maybe gives less than the risk-free and is also risky. Okay, so we can somehow safely assume that mu is larger than r. If this is the case, we have that under P, the log prices has a normal density centered on a mean which is larger with respect to the mean under the risk neutral measure, because mu is larger than r. But if this is the case, now consider the following. I can always consider an event, and an event for me can be the probability to be in the money at maturity. Now, given the connection between the normal and log normal distribution, the probability that log of S capital T being larger than log of K under P or under Q corresponds to the probability under P and under Q of S capital T being larger than K. So this is the event to be in the money or at the money, but at the at money part, if you want, is irrelevant because the equal sign under continuous random variable is not that particularly interesting situation. But in any case, we are considering the probability to be in the money under the physical measure and under the risk neutral measure. Now, since under the physical measure, my normal distribution is on the right-hand side because it has a higher mean with respect to the normal distribution that has the mean under the risk neutral measure, it's not difficult to see that the probability to be in the money, that is the probability of my log prices to be above the log of K, or my prices to be above K, since K is a fixed quantity, the probability to be above under the physical measure is larger than the probability of being above under the risk neutral measure. So just looking at this, and it will be also clearer when we consider the Wang transform under the risk neutral measure, we underestimate the probability to be in the money. This is something, in a sense, nice, because obviously it means that in the real world, our chances to be in the money are higher than in the risk-neutral world. But since the risk-neutral probability to be in the money also appears in the pricing of, for example, a European call, then it also has an impact on the representativeness of the price that we compute under the risk neutral measure in terms of the physical measure. So it's always very important to understand how the different measures are connected. And with the Wang transform and the Lorenz curve, it would be immediate to see how they are connected. Now, as I wrote here, just notice that it is something that we will later observe, is that unless I assume mu to be equal to r, but again, this is something that we can safely exclude, then the ratio between the probability to be in the money under P and the probability to be in the money under Q cannot be 1. Okay, this is also one of the justifications of the use of the Gini index, but you will find more details in the readings on right space. Now, we can easily verify, as I showed you in the previous lesson, that the probability to be in the money under the risk neutral measure is nothing more than a transformation of the probability to be in the money under the physical measure. But this transformation that we have considered is what? Is a Wang transform. It's a Wang transform that, in particular, if you remember what I told you last time, is convex. It's convex because we are considering as argument of our CDF of the standard normal the quantile phi that represents the part that inherits the probability, minus C. And C is that term that includes the Sharpe ratio. Okay, now the Sharpe ratio, since we're assuming mu to be larger than R, otherwise, again, I repeat, will not make any sense to invest in the risky asset. Since mu is larger than R, the quantity that I called here C in the slides is positive. So I'm taking the CDF of normal computed in the quantile of the normal minus a positive quantity. So as I told you last time, in this specific situation, this Wang transform gives a convex function. But it's not difficult to observe that this Wang transform, that in this specific situation is convex because the quantity C is positive, is nothing more than the Lorenz curve generated by some log-normally distributed random variable. And given the Lorenz curve, I can compute the Gini index that you see on your screen. Now, an immediate question that I can ask myself is, okay, this is a Lorenz curve associated to some log-normally distributed random variable, but what is this random variable? Is there a way of coming out understanding what is the random variable? And actually it is, once we remember that C is nothing more than the sharp ratio multiplied by the square root of capital T, so the maturity. At the end of the day, we can easily verify that the random variable that generates the Wang transform, if we read the Wang transform as a Lorenz curve, and that is also the connection between our P and our Q measure, is nothing more than a Radon-Nikodym derivative. And the Radon-Nikodym derivative that we consider is our Z. So Z capital T, which is equal to the exponential of lambda B capital T minus 1 over 2 lambda square capital T, where lambda is the sharp ratio. And our B is our standard Brownian motion under the physical measure. Now, an interesting thing that we can observe is that once we know that, so once we specify the C term, that for us is, again, the sharp ratio that we quickly call lambda, and we multiply that by the square root of T, the Gini index becomes what you see on your screen. Now, it is not difficult to verify that the Gini index in this framework in which the Lorenz curve of our log-normally distributed random variable, which is nothing more than the Radon-Nikodym derivative connecting P and Q, then acquires an interesting meaning. So the Gini index becomes a measure of the distortion between P and Q. And we can obviously observe two limiting situations. The first one is that now it is not difficult to verify that the Gini of our Lorenz associated to it is not difficult to verify that the Gini index, G lambda, associated to our Lorenz curve derived from a log-normally distributed random variable that at the end of the day we know is the Radon-Nikodym derivative connecting P and Q, okay, this Gini index acquires an interesting representation in terms of measure of the distortion between P and Q. Now, let's start by considering two extreme cases. We know that the Gini index can be equal to 0 and 1 in the limiting situations. Now, when Gini is equal to 0 in this specific situation, it means that the argument of our normal CDF needs to be equal to 1/2, because then we have 2 times 1/2 equal to 1 minus 1, 0. Okay? But when can we observe such a situation? Such a situation is easily obtained when, for example, the two measures P and Q are the same. And that situation is when mu is equal to R. In fact, if mu is equal to R, then the lambda parameter there, which is our sharp ratio, is mu minus R over sigma. But then mu minus R becomes mu minus mu, or R minus R, as you want to write. We are assuming they are the same. So the numerator is 0 divided by the standard deviation is still 0. The argument of our CDF of the standard normal becomes 0, and a standard normal in 0, when we consider the CDF, is equal to 1/2, okay? Because it's a distribution which is symmetric with respect to 0. So in 0, we have 1/2. So in the case in which our g of lambda is equal to 0, it means that the sharp ratio is equal to 0, and essentially it means that our two measures, P and Q, are the same. So there is no change of measure because our mu is equal to R. So there is even no necessity of substituting mu with the risk-free rate. The opposite situation is when the Gini index is equal to 1. Okay, when the Gini index is equal to 1, essentially it means that the CDF part of the formula goes to 1. Then 2 times 1 minus 1 equal to 1. Now, when can we have this situation? There are different possibilities. The first is that there is a very big difference between mu and R. So if mu is very, very, very much larger than R, we are tending to this situation. And this also tells us that in the situation in which the implicit return of a risk investment, mu, is very different from the risk-free rate, so we are considering something which is potentially very nice for us. At the same time, by considering the risk-neutral measure, we introduce a very big distortion of probabilities. They still agree, P and Q, on what is not possible because they are always equivalent, and this comes from the fact that Q is a distortion of P and vice versa. But on what is possible, they can give very, very different results, very different probabilities. So the more mu is far away from R, the more our Gini index increases and tending to 1, which is the limiting case in which essentially we have the two probability measures are equivalent but maximally distorted. Another situation is when, for example, volatility goes to 0. Now, look at the small graph I'm representing here. Now, this is a very simple representation. I'm considering two normal distributions, each one with its own mean. But we know, for example, coming back to what we have seen before here, that if we consider the log prices under P and under Q, they are normally distributed with the same standard deviation and just different means. Okay, what you see in this graph is just a very simple representation of the same problem. So we maintain the standard deviations fixed, more or less, in my graph, and we have two means. I'm not saying, so allow me to say that this is just a very short way of writing the thing. So I'm not saying that the two normals are centered in mu and R. So they are centered exactly in the same quantities that we have seen before, and the difference in the two quantities are mu and R. Okay, so if you want the first normal distribution, it's centered in the log of S0 plus blah, 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 and the R term, and the other one on the mu term. Okay, is just a way of writing shortly without copying the entire value of the mean. But for sure, we know that since we have mu larger than R, and we can safely assume that, then the distribution moves to the right-hand side. And this is also another way of looking at the fact that the probability to be in the money is underestimated under the risk-neutral measure with respect to the physical measure, if you want. Now, assume that sigma is going to 0. So we have these two distributions. If sigma is going to 0, it means that they become more and more concentrated on their respective means. So it means that the intersection between the two densities reduces. So they tend to give more and more different results for what concerns what is possible, and given that for what is not possible, they continues to agree. Conversely, if I take sigma growing to infinity, what you have these two normal distributions that open, 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 and spread to the fact that they go down, they stretch so much that at a certain point it becomes very difficult to distinguish them. And we go back to the previous situation of a Gini equal to 0. So if you want, Gini equal to 0 can also be obtained when sigma is essentially so big, then it becomes almost impossible to distinguish two distributions, two normal distributions like these, even if they have different means. If the standard deviation is very big, no test will be able to tell you what the difference is. The third situation that we can consider, but then we can also consider combinations. The third situation that we can consider is when t is going to plus infinity. Now, we know that when t goes to plus infinity, the more the time, or the longer the time horizon, the more the uncertainty. So obviously, every time you change your measure, if t goes to plus infinity, we have that essentially the Gini is telling you that there is a very, very big difference between the two measures. And that comes from the fact that in a very long time horizon, the uncertainty is so large. Maybe we are even in front of situations of ambiguity, unknowledge, to use the Shackle term, of Knightian uncertainty, to use the Knight term. So uncertainty is very, very large. And it's very important to observe that in this framework, the Gini clearly tells us how the two measures are connected and distorted. It's a synthetic way of understanding how distorted one is the version of the other. With Lorenz curve, conversely, that in this specific case is also Wang transform, we have a more rich representation of the exact connection between P and Q or Q and P. Okay? A nice graph that I like to show you, which is not very commonly found, is the following. Now, imagine that we start from the unit square that you see on your screen. Now, this unit square is the square where we have our Lorenz curve that in reality lives in the lower triangle, but it's not a big deal. Now, Lorenz curve connects a value p that in the inequality studies is the percentage of the population, but you agree that this is a value between 0 and 1, so we can read that as a probability. And the Lorenz curve gives a value which is again between 0 and 1 that again we can read as a probability. Now, in this graph, we essentially see the connection between the measure P and the measure Q. So the measure P will give a probability for a given event, okay, which is P star, for example. Given P star, I can always go on my yellow line, which is the Lorenz curve, and I can find the corresponding value Q star, which is the probability that measure Q assigns to the same event. Only in the case in which the Lorenz curve, the yellow curve, coincides with the perfect equality line, which is the diagonal, I will have that P and Q will give exactly the same probability for the same event. And in fact, if we assume that mu is equal to R, so there is no distinction between probability P and probability Q, then we know that, for example, the probability to be in the money will be the same under both probability measures. So it's quite trivial. But unless we consider this specific case, which is also the case in which Gini, which is now the area I dashed in green, is 0, apart from that situation, they will always disagree for what concerns the masses of the events that are possible. Once I have this plot, I can associate to the plot what? I can also associate to the plot the CDF, or if you want, the quantile functions. So you can always read both things in the different ways. In this specific case, essentially, if you consider P, we look at the quantile function. So given a probability, look through the function that you see goes down like this, so the quantile function, I can find the corresponding critical value for that specific probability. And in this way, we see that we can easily connect the two probabilities. Now, this quantile function, or if you want to give the CDF representation, will be the same, are obviously dependent on the random quantity that I'm studying, okay? It can be the log of the price. It can be any other transformation of the price. They can be the returns if I'm interested in the return. But at the end of the day, the connection is exactly this one. For a value P, that, for example, is P star on this plot, I get a value Q star. And given P star and Q star, using the quantile functions, I can get XP star and XQ star. So these are very important because immediately it tells us that it's not guaranteed that for a probability of 20% under the physical measure P, I get the same critical value under the risk neutral measure Q, which is exactly another way of telling what I already told you several times, that is to say that if we consider the basic framework of the geometric linear motion, Black-Scholes-Merton, and blah, 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 under the risk neutral measure, we tend to underestimate the probability to be in the money because we are fixing the quantile that depends on k, and then the probability will be different. If we, on the contrary, want to do the same stuff by fixing the probability and looking at the quantile, what we will find is that for a given level of the probability, I will get different quantiles under p and under q, which is the other side of the coin. Now, this plot connects the two measures, and if you want, in the plot is not present, but we also can consider the opposite situation, that is the situation in which instead of Q equal to P, we have the maximal distortion, so the situation in which the Lorenz curve tends toward the perfect inequality, which is also the situation in which the Gini index is equal to 1. In that situation, I leave to you the graphical representation, but you see that the distortion between P and Q is essentially maximal, because they are still equivalent, but they possibly disagree completely on what are the masses of the possible events. The results we have just considered can be somehow easily generalized. So let's consider, for example, a slight modification of the geometric linear motion as the one that you see on your screen. By the way, this is a process in which mu and sigma are now functions. They are no longer fixed parameters, but they are deterministic functions. So there is no randomness in them. Okay, so mu and sigma t are deterministic functions. I suggest you to try to solve, for example, as a good exercise, the value of a European call or a European put using this process instead of the geometric linear motion. Okay, if you use this process, it's a little bit more cumbersome to perform the computations, but at the end of the day, as you see on your screen, the connection between P and Q, or in specific case here, between Q and P is exactly the same type of connection, is again a Wang transform, but now the C term, so the minus C term, is no longer just, for example, the Sharpe ratio, or again, it is implicitly a Sharpe ratio, but it's no longer the nice Sharpe ratio we have seen before, but it's a little bit more cumbersome object that involves integrals. Okay, but at the end of the day, the message is the same. The connection is qualitatively, let's say, not quantitatively, but qualitatively of the same type. A second important distortion that we can consider is then the one that we have already seen in the European call. So we know that at the end of the day, this is our pricing formula. We know all the different components, and we know that and we know that inside this formula we can observe two different probabilities of the same event to be in the money. Okay, one is the probability under the share measure or the stock measure or the price measure, as you want to call it, and one is the probability under the risk neutral measure. Now, an interesting thing that we have observed is that the connection is again a Wang transform type. And in this case, we can actually also say more, because the connection between Q and P is, Q and D, sorry, is for sure a Wang transform and is convex, so it's also Lorenz curve. The connection between D and Q, there is a typo here, so here this should not be a D, but it should be a Q, sorry. So obviously D of to be in the money is phi of phi to the minus 1 of q, otherwise it makes no sense, this formula. So the second d should be a q. In the second formula, we have that the Wang transform is concave. And since it is concave, it cannot be formally represent a Lorenz curve, not at least in the very basic definition that we gave. It is, nevertheless, the line-Euler curve. And what I can tell you is that all the quantities that we have defined under the Lorenz curve, like the Gini, can also be expressed under the line-Euler curve. And so at the end of the day, we can still give the same type of interpretations, okay? But just to be pedantic, in the first case, we have a rank transformation, which is also immediately a Lorenz curve. In the second case, we have a rank transformation, which is not a Lorenz curve, but it is a line-Euler curve. But again, I can compute my Gini and blah, blah, blah. Even more, a very simple exercise. Consider the first transformation, that is to say the connection between Q and D, via the Wang transform that you see there, where the C term is represented by sigma square root of t minus t. What is the Gini associated to these transformation? Compute that. You know what is the Gini of a log normal, so it's not a big deal. Compute that. Once you have that Gini, try to give interpretations on how the two measures can be the same or different depending on the different parameters that are involved in our computation. Again, you will see that sigma necessarily is very important, but is not the only relevant quantities. And again, you can easily quantify which one of the two measures, for example, underestimate. So you fix one of the two, like say Q, and you can try to answer the question, does D underestimates or overestimates the probability to be in the money in this setting? It's a nice exercise. And if you want, always starting from the Lorenz curve and always starting from the associated Gini, again, I'm just speaking about the first of the two equations, just to keep things simple. It will also work for the second, once you correct the D with the Q, okay? But just focus on the first one. If you consider this one, another thing that can be nice is to try to obtain the Radon-Nikodym derivative that connects D and Q. And again, you will see that is obviously so an exponential martingale, a log-normal distributed random variable. It's an interesting type of Radon-Nikodym derivative, so it can be a nice exercise to derive it. Okay, so this is the end of our class for today. I hope it was interesting for you. For sure, these are things that are not commonly found in textbooks, so I think it can also be nice to have this type of knowledge. And later in the course, you will see that we will be back to these type of things to give more interpretations to the different changes of measure and the impacts of that. Because, for example, knowing that the risk-neutral measure underestimates the probability of being in the money has an impact on the pricing formulas, on the different pricing formulas. In the European call, as I told you, it's quite clear to say that maybe I did not tell you actually what is the impact in the European call, but that was on purpose. It's a nice exercise for you. So try to see what is the impact of changing the measure in the pricing formula. What you have to do is just to, if you want, keep the D part fixed, substitute P with Q, substitute Q with P, and try to understand how the price changes. It's not a very difficult exercise. So I think that it's totally something manageable for you. See you in next class, and again, be safe and sound at your places.